of you. I see some familiar faces, and I'm really excited to talk about Google Earth Engine. How many of you have heard of Google Earth Engine? Wow, that's a big number. How many of you have used Google Earth Engine? Great, so maybe half of you. So for those who have not used it, the first part of the presentation, I'm going to give you some history, why Google built this platform, what it can do. And for those who use it, maybe I have some recent examples and advancement that you may not be aware of, and I'll show you some interesting ways that people are using Google Earth Engine, right? So let's get started. I generally like to keep the presentation very informal. Feel free to raise your hands, ask questions, and we'll have some Q&A and discussions at the end, right? So Google Earth Engine is different than Google Earth, right? When in early days, the Google Earth was launched, there was Google's first geospatial platform, and that kind of changed the whole geospatial industry. Everybody had access to high-resolution imagery at their fingertips. You could just have, open up Google Earth, look at anywhere in the world, and you can see high-resolution imagery. And once it was launched, people started using it for kind of interesting purposes. This is a screenshot of Google Earth, not Google Earth Engine. Back in the early days, there was a feature called historic imagery. You could go back in time and see what the snapshots of high-res imagery. And people started using it for interesting purposes. So this is showing Amazon rainforest, and over multiple years, you can see the deforestation happening. And people who were kind of living there, who were kind of trying to protect those forests, they saw this and say, hey, this is very useful. We are now able to see where the deforestation is happening. But the high-resolution imagery were available, say, once a year, or even not regularly. They say we are able to see the deforestation after it has happened. Ideally, we would like to stop it when it's happening and do something about it. So they were trying to tell us that can you build some tool that is not just visual, but you can give us some analytics. Can you give us a tool that we can track deforestation, not just visually see? So there was a lot of demand like that was coming up. So Google started looking into this problem, say, how can we do it? We already have Google Earth. What can we do more? And for solving this kind of problem, deforestation at a global scale, there was already a lot of data available. So this is just a NASA satellite constellation that is operational. And there were multiple other satellites that were collecting data from space for years together. And all of this data is available publicly. So Google said, OK, there is all this data available. Can we do something about it? And this kind of fit right into the mission for Google. Right? Google is its mission is to organize information. And if you ever work with any of the satellite data, it's very hard to use. Right? It's at different places. If you want to use two sources together, it's hard. If you want to access it, though it's free, the amount of data the speed you need and the storage you need to download data is humongous. Right? So it's not easily accessible. And even today, if you're doing remote sensing, it's hard. Right? Though the data is free, it's so large that downloading, processing, it's not easily accessible. So Google said, we have the technology and capability to kind of address this problem. So they're saying, how do we do this? So when we start building out this platform, what do we do? Should we build a desktop-based solution, like, say, ArcGIS or DAS Imagine that all of you are using, just with a kind of better technology like Google Earth? That doesn't work, right? Because remote sensing data is large in nature. Processing it requires much more power than your desktop. So Google took inspiration from this very influential book. This is ex-Microsoft research head. In this book, they hypothesized that there have been multiple revolutions along the scientific progress. And we are in this kind of new paradigm where you might have heard buzzword big data, right? So we are in this paradigm of big data, and the tools that we need to address scientific problems in this are very different. And this quote says it's often easier to move your questions to the data than your data to the question. Right? In our context, what that means is rather than downloading data to your computer, processing it locally and asking questions there, it's much easier in the realm of big data to have your data and computation together in the cloud, where you can ask questions where the data is. and get the answer. Right? So that's the architecture that Google Earth is built on. So what do you need to build this? Right? First thing is need data. And you can see the remote sensor data is so large. Google Earth Engine has a catalog of daily updating data sets, and all the way going back to the history. So for example, Landsat, from 1980s onwards, we have every scene in the cloud accessible to anyone, right? When we started doing this, even the archive was so large that USGS had it on tape. If you wanted some scene, you write to them, they will pull up the tape, upload the data, send you an FTP link a few days later. Right? So first thing Google is, we went to USGS, got all the tapes, copied all the data to our servers, and say now it's available to anyone. Just that, you can download it, you can access it just by specifying what you want to do. Right? And that's not only enough. You have historic data, but you need to, as the new scenes are being produced, we automatically download, process, and make it available. So if you're building some application where, say, you want to track deforestation, right? You don't want to, you want very real-time information. So as soon as a new scene is produced by some of our partners, we get it, process it, and make it available. And you can see there's 30 petabytes of data already in the catalog. And once this is there, you don't need to download it or process it ever again. You just say, I want to use this data, I want from this date range, and I want to apply this process. And it just works. Right? And we also have the ability to upload your own data. So if you have your data sets that you want to keep it private, or it's not there in Google Earth Engine, you can upload it and use it along with this data. Right? So another problem this solves is, it's a single catalog. That means you can use 2 data sets from 2 different sources together. Don't need to worry about projections, different resolutions, etc. Google Earth Engine takes care of all of that. Right? And we have a lot of new requests as scientists and researchers are starting to use this data sets. They say, oh, I need some climate data. Can you, upload some climate data? If it's open data, publicly available, we would just add it to the catalog. So you don't need to worry about it. Right? Yeah.
Suppose the same data is available in information available in USA. Regarding same topic, some information available in Israel, some information available in India. We are putting all the data here. So finally, it is accessible to everyone, but it is not the authentic one.
Yeah. So
how can clock check which is the real information as a user?
Good question. So, the question is, how do you validate this data set? What is authentic and what? So we rely on the publishing agencies. So as a user, that's up to you to decide which data you want to trust. If it's publicly accessible and it's a authentic data source, we put it out there. For example, USGS. Do you trust USGS satellite? Yes. Everybody trusts Landsat. You trust Sentinel. You trust ESA. We put the data there. Now, if there is a mismatch between a Sentinel scene and a Landsat scene at the same rate, that's up to the scientists and to figure out. We don't process or change the data sets. As the data set is there, we put it and make it accessible to you, right? How do you validate that? That is a user end problem. We'll give you the tools and the data set to help you validate that, but that's again, if you want to do research and find out, that's the thing you have. So, we can just stop saying, oh, all the data is there. We have solved the problem. Go and do your amazing science, right? But that doesn't stop there, right? Imagine you want to do some computation on a terabyte of data, right? You start your process on a computer, it's going to take you days. It's not easy to find very fast computer. And even a moderate size computation, say if you want to do some computation for a state level, it's going to take you days or weeks to do it. It's not easily accessible, and downloading and processing data locally is not something that is very fast. So we put our computing power alongside the data, and that is the critical part of why Earth Engine is so fast and so useful, because it's not only data set, it's also the computing power. They are co-located. So Google has very large powerful data centers. We make it available to the users along with the data. So the data and the computation resides together at the same place. But is that enough? We say, oh, you have 50,000 computers with all the data, go and do something. It's not enough, right? We need some way to specify what processing you want to do, right? So we've built something called an API. It's a way to specify what programming you want to do, what computation you want to do using the data and the CPUs you have, right? You can We have a JavaScript and a Python API that is officially supported, that you can write your code, say, I want to calculate NDVI, I want to do this aggregation, and I want the results. So you specify that. At the back end, we go use those computers, use this data to do that computation and give you the results. Okay? So Google built this, the early versions of the search engine, before it was even kind of widely available. We had the system. So what's the first problem? We thought, what's the first problem we can solve? So clouds, anybody who's worked with satellite data, clouds are a big problem. So we said, can we do something about it? This is the most cloud-free scene over Andaman Nicobar Islands in 2019. Now imagine, this is the most cloud-free scene. What a regular scene looks like. So clouds are a big problem. Imagine you're studying this area, or you're doing some research here. You're out of luck because the clouds are a problem. But the good thing is, this is a Landsat scene. Every 16 days, or now every 8 days, you get a new scene. The clouds are not at the same place. The clouds and the cloud shadow will move around. So if you just do a simple computation where you say, let's take all the scenes captured during 1 year. For each place, let's take a median value of a pixel. Because the clouds will be bright, shadows will be dark. A median value will be probably a cloud-free pixel. And since we have so many scenes, there's a good chance that there's a cloud-free pixel. It's a simple kind of idea, and we said, let's try it. So suddenly you can now see through clouds. This is a 1 year composite of the same area, right? So now this is very powerful. From this, you get to this. You could do this in any other software, right? You download all the scenes, do this. But now we have Earth Engine. We had all the data for last 35 years. We had this large computation cluster. We had an API. So we said, can we do the same for the entire world? Now that's a problem that requires a lot of data processing, a lot of computation. It's not easy. But since we had Earth Engine, we tried it, and this is the result. So this is the first ever high-resolution cloud-free composite that is global in nature, right? This became known as Pretty Earth, and if you use Google Earth or Google Maps, this is the base map you see as you zoom out, right? This is not a real picture, right? It's summer everywhere, there is no cloud anywhere, but still very useful, because getting a global picture of the cloud-free nature at the same scale is very useful. But do we stop here? We said, this is only 1 year. We have 35 years of data, right? Can we just run it for all 35 years? And we ran this, and that resulted in a product called time-lapse. And with time-lapse, it's a globally zoomable video that you can see how a landscape has changed over 35 years. And since it's cloud-free, you are able to see year on year where changes have happened. And this by itself is very useful. I'll show you some examples in India. So this is, if you go open time-lapse and go to this region, you can see this huge forest loss that's happening in Assam. This is the region where there's a Bodo conflict, and you can see the deforestation that's happening. And this is over a large time span. And if you wanted to kind of see this in action, it's very hard, because you'll have clouds, your data will be kind of messy, there'll be missing strips. But if you do this kind of computation, you have a cloud-free mosaic, year by year, you can see this kind of changes. Another interesting urbanization, you can see this Greater Noida, can see the development that's happening. And since it's over a large period of time, you can see the rivers changing course here. A lot of interesting phenomena that you can see, which you were not able to see before. Our own Bangalore, this is the Bellandu Lake and the outer ring road being constructed. You know why this lake is now having so many problems, because we have built a highway and urbanization on the lake bed, right? So again, this kind of phenomena is, you can now see, this is a free tool that's available to everybody. You can use and kind of see this. You can export videos and show it to people. This is another example of kind of a dam construction. The point here is, this is cool, but the point here is, this would have been impossible to do it with a traditional tool set, right? Using Earth Engine, if you say you didn't have Earth Engine, you wanted to do this, first you need to find something that holds a petabyte of data locally, right? So you find a large enough hard drive that holds a petabyte, then you start your computation. If you have the most powerful CPU, a single CPU, and you start a process, it's going to take you 200 plus years to do this. But since we had Earth Engine, we could do this in parallel across so many machines. We finished the computation just over a day. And the point is, this power is available to all of you. today. Right? So now you can think big. You are not limited by the availability of data set and computing power. Right? So this opens up a lot of possibilities for doing a kind of research or science which was not possible earlier. And I'll show you some examples of what this happened. So what is Earth Engine? Earth Engine is not one thing, it's a system that consists of data. The data catalog by itself is a very useful product. We have continuously updating pre-processed data from multiple sources. Right? That itself, a lot of people, for example, if you're doing some work and you need data, this will probably the easiest place to get processed data in any projection, in any area you want. Computation, as I told you, we have massive computation attached to the data. There's an API, and there is some IDEs, so there are ways to call that computation. And I'll show you some example. We have something called a code editor. This is a browser-based tool where you can go type some code and use Earth Engine. We have Colab notebooks, it's Jupyter notebooks. You can type some Python code, call Earth Engine, and there are other systems that are available. So how does it work? Brief, high-level overview of Earth Engine. You can think of this as the data center where Earth Engine is there, right? So from a front end, so from a code editor or from a Jupyter notebook or from a third-party client using the API, you type what you want. And the language you type in, JavaScript or Python or R, that's irrelevant, right? It's just a way to specify what you want to do. So use the Earth Engine API to say, I want to compute an NDVI. You can specify it in multiple ways. And your code editor, your Colab network will translate it to a request that Earth Engine can understand. And regardless of the client use, the request is the same. And that's why once you learn how to use Earth Engine, you can use any programming language or any platform you are comfortable with, and it's kind of the same model that works. So the request gets translated, so your browser or your local client, you're typing some code, that gets sent to the server as a request to Earth Engine. It goes to the backend. The backend has access to a whole range of computers. It has access to all the data, and it's got access to all the functions. So there are primitives. It knows how to do, say, an overlay, how to do a composite, how to do a spatial join, all that kind of geospatial primitives that is there. It knows how to do this. And this request is then fanned out. So a lot of the main advantage of using Earth Engine is it does computation in parallel across multiple CPUs. So once you do a request, it breaks it down, sends it across multiple systems. And each computer gets a request saying, hey, the user asked me to compute an NDVI. This is one tile, so it'll say I have access to this small tile. I know how to do NDVI for this tile. I will do the computation, and once all the computers finish, it gets combined and say, oh, user just asked me for an image, so I'm going to return an image, which is an NDVI image. Or the user asked me just what's the average NDVI over this area, so I'm going to do and send back the number, right? So imagine you wanted to just get a value. You say, I want to get what's the average NDVI over last 30 years. So for that, it may have done a lot of computation, used terabytes of data, but the result you get back is a number. And this is what you want. You can say, I want to see those results, see those images. You get the images, right? So all the computation happens here. You never get all the source data, raw data back. You get what you asked for. So that is very small amount. So that's why you can kind of, when you work with everything is very fast. Because you say, I want to do this computation. A huge cluster of computer does the computation, and you get the results very fast, right? All good said and done, let me show you some demos, right? So you can understand the system, and then we'll dive into what people have done with it. This is what Earth Engine looks like. For most people, this is the browser-based code editor, right? This is a system where you can interact with Earth Engine. You can just go to code.earthengine, go to google.co.in, and start using Earth Engine. This is where you type code, right? We have a lot of documentation. Sai, in the later session is going to teach you some of how to write Earth Engine code. But once you type this code, click run. It's going to send the request to the backend. It's going to process. If you asked for a map result, it's going to show at the bottom. This is the map interface. If you ask for a number, it's going to show at the right-hand side, which is the console. You can save your scripts here. So Earth Engine, when you write code, we save it as a script. Right? So this is a kind of a integrated environment where you can run some code, get the results. There's a way to even export data out of this here. Right? So here, I'm showing a simple example. I have one scene over Bangalore. I knew the scene ID from Lancet. I just say, I want this scene. Simple enough. So this is how I can say, I want this image. And then I say, I want NDVI. So as I say, I want NDVI, you can see it's processing, right? So live, it sent the request. This is one Lancet scene, I want NDVI. Went to the backend, I got the computation, I got the results back. And all the computation is done at the zoom level you are in and at the viewport you are in. So that's why it's very fast. It didn't do this computation at 30 meters per pixel. It did at whatever zoom level you are. But if you want more results, what you do is just zoom in. And it's going to get you new results at that level. And it's all happening real time. So gone are the days where you start some computation and say, oh, it's going to take half an hour, I'm going to grab a coffee and come back. It's all real time, right? Yeah.
What will be the maximum zoom we can do? Will it show the street map also?
So background map is a Google map. You can see the street map, but I'm loading Lancet data, which is 30-meter resolution. So it's not a very high resolution imagery, but it's a medium resolution imagery. So whatever data source you have, if you have high resolution image, you can upload and use it along with this. Now I'm not impressed. I can do this, I have ArcGIS, I can also do this very fast, one scene. But the point now is, I can ask Earth Engine, say, give me, so this is what I'm doing here. Give me the full Lancet collection for a year, globally, and give me a composite everywhere. So as I ask this, some people are going to cringe. I'm processing terabytes or petabytes of data, but as you can see, it's processing. The tiles are flowing in real time. If I wanted NDVI or if I wanted the scenes for a different part of the world, I just zoom and pan, and you can see it's computing. And in a minute, all the tiles are going to start coming back. You can see this is the yearly composite of Lancet data that I'm getting it. And now I can just run NDVI on that. So I can just say, give me NDVI. So with just 30 lines of code, not even 30 lines, 6 lines of code, I've created a global NDVI layer for 2019. And you can see the NDVI will get computed. It's all happening real time. If I wanted to change the parameters, I change the band ratio and say I want NDWI, it's going to be equally fast. Right? So you can see that the NDVI is getting computed. Yes. So question is, can you take the output out? Yes, of course. Earth Engine is a very open system. We know that when you're working with this kind of analysis, all the analysis may not be possible. You may want to export this data to, say, R or Excel or ArcGIS and do some further processing. So all of the processing you do, all of the source data and processing, you can export it in any form you want. So if you want to export image, you can say export this region or the entire thing as a GeoTIFF. It'll go in your Google Drive, and you can download this GeoTIFF. If you are doing some computation, you can say save it as a CSV. Or if you have vector data, you say save it as a shapefile, download it. Right? So everything you do, it's completely downloadable.
Apart from NDVI, is there any other indexes also added?
So the way you can see the way we are doing NDVI here.
So we can change the band number.
We are just doing it saying, give me a normalized difference of 5 and 4, right? So this is a function. It's like you're programming in Python and say, I want ratio of these two bands. Earth Engine provides you the functions to do whatever computation you want. This is just an example saying, if you want an NDVI, just call this function on this data set and you get the results, right? Yeah.
Can it be used for commercial applications?
So right now, Google Earth Engine is available free of cost for non-profit research and academic purposes. There is a pilot that is going on for commercial use. The Google Earth Engine is integrated with Google Cloud. So it's a part of Google Cloud product. If you are interested in commercial use, you can sign up for a trial and use it. And we've not announced what's the kind of going to be the cost for commercial application. But for academic research, non-profit use, is going to be free. default projection system is, the way Earth Engine works is the source data is in whatever native projection it is. Right? So when Landsat data is there, we just say load it in whatever projection it is. When you do the processing, you always ask what's the projection you want your output in. So in this case, we say I want an output as a map. And this map is a Google map, so it's a Mercator projection. So we say I want your output in the Mercator projection. So Earth Engine implicitly goes behind the scenes, reprojects all the data to that projection, does the computation there. When you're exporting the data, you have to always specify at what scale and what projection you want your output in. So when you've done all this analysis, you loaded some MODIS data, some Landsat data, you uploaded some shapefiles, do all the analysis. When you export your results, you say, I want my final geotiff in EPSG 4326 at this scale. And it'll reproject everything and give you that results. So when you're using Earth Engine, most of the time you don't really have to care about projections. You can work with multiple projection data together. And that's again one of the benefits of having a system like this, that the system takes care of all this data munging that you have to do when you're doing remote sensing. Right? Yes. Yes, so Sentinel is one of our most popular collections, and if you saw the presentation, half of our kind of collection size is the Sentinel-2. So we have the TOA data, raw data, TOA data, and the surface reflectance data also. So atmospherically corrected data also available, and it's available as soon as the ESA makes the new scene available, we download it and make it available. So it's a full Landsat collection, Sentinel collection, Sentinel 1, 2, 5 is available. We have different sources from different regions. For India, I think the best you get is Sentinel-2, which is 10 meters. We have some, USDA imagery, which is 1 meter for US. But the one requirement, so a lot of people ask, like, I want to export my data. So one requirement for us to allow you to export any data is that the data has to be under very open terms. So all the data that is freely accessible, freely usable, under very liberal license, we put in Earth Engine, so that we can allow our users to export and do whatever you want with data. So if you imagine Google has access to, say, high resolution digital globe imagery, but that is a licensed data. Digital globe says you can't allow people to export it, you can't make people do derivative products. If you put in Earth Engine, we have to put the restriction. Oh, you can just view it, you can't do anything with it, right? So that's why everything in the Earth Engine catalog is whatever is publicly available. But if you, say, bought a high resolution scene, you want to use it, you can upload it privately, use it alongside with other data sets privately, and use the same computation. So computation is given to you, but you can upload the data yourself privately and use it. Yes?
Yeah, for example, I procure 0.3 meters spatial data. Say, for example, for Karnataka, I want to do the natural resource mapping for the state. Can I use it with this? Okay, only thing the license is given to me. I only use it for my state. But only thing is I use your engine for deriving the natural resource mapping of the state of Karnataka.
Perfect, that's a perfect use case. So if you have this data, you go here and say new image upload geotiff. You upload a geotiff. By default, it uses the same sharing model as Google Drive. So by default, it's a private. It's like your Google Drive document. It's private to you, but it's accessible within Earth Engine. You can use it by itself, use the competition, Google Cloud competition, free of cost. And also, if you say, I want to do some validation with, say, MODIS data or Landsat data, you can pull that from Earth Engine, combine it, and use it. And you can export whatever results you have privately. If you are working with a research group, you can say, I want to share it privately, but among my research group. So you can share with those people.
Yeah. Now, if I want to derive the land cover map, say I'm on 2000 scale, what would be the level of accuracy which I could be able to get it from this?
So it really depends on source data. This is the processing system. So you replace Earth Engine with, say, ArcGIS. What's the answer to your question is whatever your source data is gives you accuracy. So the processing functions are well implemented, well documented. So if you say, how do you do, say, a band ratio, that is standard, algorithm. So it implements all the standard algorithms. You can specify the computation. The results will depend on your processing and the source data set.
Because the NVIDIA is basically, we have a lot of algorithms. While the land cover actually, there is a lot of diversity here.
Yeah, so for land use land cover, you would probably use some of the classification. So these are all the classification algorithms that are available. So you want to do, say, supervised classification for land use land cover, right? So there is an algorithm for, say, you want to use cart algorithm, right? So this is again a standard classification algorithm that you use. It's documented. There's a reference to the implementation that this is how it's implemented. You have all the parameters. You choose the parameters, run your classifier on that. And as you learn in the next session, now you can, if the more modern way to do this, you use more machine learning techniques. You build a neural network in Tensor Flow, and you can apply it on this and do your classification. Right? So there are multiple techniques available. What Earth Engine is like a platform. It allows you to run different kinds of computation on this data in a scalable way. Right? Yeah.
Yeah, since I have been using fusion tables to export my data and import it whichever data I have created on Google. But now the support is stopped since 3rd December last year. So what's the other way to use my
Fusion table was when Earth Engine early days, the way you use vector data was through fusion tables. We have a much better vector solution. I'm going to show you that. It's very simple. You have vector data, shapefiles, upload it to Earth Engine, and you export it as shapefiles. So there is a built-in shapefile support, which is much more widely accepted support vector format. Yeah.
We have been using Earth Engine so far. So whatever the libraries are available, analytics are available, we are using that. But to continue this question, we have some query concerns, some accuracy concerns. So in that relation, we wanted to develop our algorithm, right? So being this platform is a parallel processing platform, I need to take care of parallelization or distribution. So whether the platform is open for design our own distribution algorithm, our own parallel algorithm, and the design algorithm will be able to upload it.
Yeah, so good question. So I want to correct you that when you implement something in Earth Engine, you don't have to take care of parallelization. Earth Engine takes care of parallelization for you. Right? So it's much easier to develop this kind of algorithm within Earth Engine than as a standalone application. So you write Earth Engine code, the parallelization is taken care of by the system. So if you want to say develop a new algorithm, you implement in Earth Engine. There are multiple, for example, people have implemented, say, a better cloud detection algorithm for Sentinel. And that is written as a function in JavaScript or Python as a library, which other users can call from your code editor and say, I want to use a cloud masking library. And you call that function and you apply it to your data. So you are able to, if you use Google Earth Engine API to write your algorithm, it is applicable to be used in Earth Engine. You don't have to worry about parallelization and other things. Right? So you can search for, there are libraries that are available. You can search in our user forum. There are multiple people who share the libraries. For Python, there are GitHub repositories of interesting algorithms people have developed that you are able to reuse easily. Yes. So there are multiple ways of customizing it. I'll show you some of those and how people have done the customization, and you can use the algorithm.
My question is, I can reuse it, that's fine, we have been using that. I wanted to contribute in the repository, so I develop it. So unless and until I define the parallelization schedule.
No, you don't have to define it. So the way you've been using it, you can just say, this is my library. There is a way to make the library available for reuse, and any other user who uses the library, they just use the function the same way you've been using.
Are you using any artificial intelligence in this process? Like, for example, reinforcement kind of a thing, or classification of this?
So we have now integration with Tensor Flow, which is our AI library. So there is an integration with Google AI platform. At the end, I'll talk about it, and there's a session later today which is going to talk about exactly how you can use Earth Engine and AI together. Yeah.
So, like, from what I understand, whenever we use the computation will be done at different pixel level or something?
Yeah, so what you are seeing is an interactive mode. So as you are, this is the best way to develop an algorithm, do your testing, do your research. As you change your code, type something, results come. Right? Once you are satisfied with the results, you say, I want to do this over a large area. You say, I want to export it. So you run it in a batch mode. So when you export some data, say, this is great, NDVI, I want it for entire India as a GeoTIFF. Now, doing that at 30 minutes is going to take time, even in the parallel mode. So you say, I want to export it. It starts an export computation that runs on servers. You start a computation, close the machine, go. Whenever the computation finishes, you'll get a new file in a Google Drive. as a result. Right, so there are two modes of doing it. I'll come to that. Will hold some of the questions. Let me finish some of the presentation. So because a lot of the questions you have, which will be answered shortly. This is another way. So we said, okay, we wanted to compute the forest loss. That was the initial motivation, right? This is the same region I showed you. There's a deforestation, and I'm just drawing a polygon and say, compute. Give me the answer. What is the total amount of forest loss? So as I do this and as I run, Earth Engine goes, gets all the images, does all the processing, aggregates this over this area and say I'm computing the number 107 square kilometers, right? So in this case, the answer I got back was just a number, but the computation happened in the server. Earth Engine started out as a remote sensing system. It's got really powerful functions and algorithms for remote sensing and image processing, but it's also equally powerful vector geospatial processing system. And this is an example I'm showing where we have a lot of vector data in the catalog. For example, all of the US Census data, roads data, all of that tables are already available. You can upload your own shape files and have this data. Once your data is there, you can do computation. For example, this is saying load all the census data and select a highway and show me all the blocks which are within 1 kilometer. So you can do this, and in an interactive mode, you can say, oh, I don't want 1 kilometer, I want 500 meters. So you run this, okay, computation happens on the server, you'll get the results flown back to you, and you'll see shortly the selection, the blocks which are within 500 meters will start showing up. Right? So again, the same concepts apply to the vector data as well. So now you have a full-fledged geospatial data processing engine available to you. And it's happening, it's processing in the backend, and you'll see this results coming to you, right? And you can imagine you have a large vector data. We have vector data sets which are millions of features, millions of vertices. You can now do this massive scale computation on that as well. So we'll dive a little bit deep into some of the systems. What happens is the key feature of the system is a collection. So a collection is a collection of images, a collection of vector features. You can apply computation, like you can say, I want to do filters. So selection, slicing the collection, saying, I want, for this date, I want it, all the scenes intersecting over my study area. I want scenes that match this metadata. You can apply all these filters. Then you can say, you define a computation. You say, this is how I want to do computation on one scene. So whatever algorithm you developed, say I have a classification algorithm, I have some aggregation algorithm, you develop, you write a function that works on one scene. So say, given one scene, this is how I'll do my computation. And then you map it over the collection. And that allows the system to be parallelized. So inherently, you don't say, this is how you should distribute my parallel computing, this many computers you use for this, that all is taken care of the system. All you say is, this is my collection of images or features. This is one function I want to apply to it. And you say, go and do it. The system will distribute all the computation, get your results together, and give you either, say, a mosaic, a table, or a chart. Right? So you can go from a collection of images to a chart using the system. We talked about this. The first mode is on-demand computation. So you are in a code editor or in a Jupyter notebook, you type some code, you get some results. Right? So this is an on-demand computation. And this is really useful to when you're developing, debugging, and it's all interactive. So when you don't really worry about computation, it's very fast interactive mode. And once you kind of done with this, you go into batch mode, which allows you to export the data. Or even, say, if you want to get a CSV, a table out, and it's over a long period of time or a large area, in interactive mode, if the computation doesn't finish in 5 minutes, you'll say timeout. So if you ever used Earth Engine, you say, I've timed out. What you do is just export the results. That will go in the back end of the system, run in a batch mode, and the batch mode has a much larger cluster of CPUs available, and it has much longer time that it'll go. There are computation which people say runs for 1 or 2 days. Like if you're exporting the entire world at 30 meter, it might going to take 2 days for processing. But that runs in the batch mode. You can close your computer and go. You don't have to keep it open running. it runs in the batch mode, right? So there are two modes of using Earth Engine. Some applications, I want to kind of highlight some of the applications that people have done specifically for India, and some of the stuff that I'm particularly excited about, some of the new features. The primary focus of the Earth Engine team is to enable really advanced research. Right? That's where the focus of the team and the system is. So we track the publications. If you just search for Google Scholar Earth Engine, around 6,000 publications, we are tracking at 50, 60 peer-reviewed papers getting published every month that use Earth Engine as a primary platform. And you can see really interesting studies that are being done. One of the recent development that happened was how when you do a research and you do some processing, the one problem you will face is, oh, I've done this, I published a paper, now what? How do I make my research useful and accessible? Right? You have some really good data set, how do I share my data set? How do I share my result with the stakeholders in an easy way? Right? And a lot of researchers say, we have done a lot of effort, give us tools to better communicate our results. So there's a new feature that was launched a year back, which is called Earth Engine Apps. So now, with just a little bit of coding within the Earth Engine code editor, you can build a user interface app. So you can have buttons, sliders, a place to display charts. And once you build an app, you can publish it on a web page. And once you publish the app, people can go to the app. You don't have to worry about hosting it somewhere, having computation. It's powered by Earth Engine. And your users can play with the data, interact, export results. And what we are seeing is most people who now use Earth Engine for doing the studies, when they publish a paper, they publish an app along that goes with it. Right? So that makes their research more applicable and useful. And even if you are in an academic setting, or if you are doing some work which you want to show your results to the public or even privately, you can build an app which allows for easy exploration of your data. I'll show some example of that. So let me just show the demos. So as you can see, the apps can be embedded within website. So this is a website that Google helped build, which is for tracking the sustainable development goal for water. The idea is to be able to track and conserve the water resources. Now, how do you help in this kind of goal? So there are data sets that are available which track the surface water at the global level. That's in Earth Engine. Now, as an end user, we want to enable the end users to say, I'm in charge of a state. Can I track the surface water for my state? Or I'm in charge of this watershed. How do I know what's been the history of water? I'm doing some effort, can you help me track it? So this is kind of an app that allows you to, and this is Earth Engine, right? But it's an end user mode where the people who have built this, they've published it. As a user, you can come in and say, oh, I want to say I'm looking at Karnataka. So I load some admin boundaries. And what is it doing is, it's looking at last 30 years of surface water history, aggregating it over the region you selected, giving you charts and numbers that you can explore in real time. And that computation is massive. If you want to do this in real time, it takes a lot of power. But since it's Earth Engine, it's happening in real time. And as an end user, you can see this kind of chart. So you can see this has been the average surface water area. I can pop it out and explore the results. Say over all these years, how the surface water over Karnataka has changed. And you can see this number, you can export it, download CSV, work with it. And if you can, here you can say I want to work at the district level. I load the districts. I can now look at the same history of the surface water over the district. So this is, again, this was a research project that was done. They want to operationalize it, help people in the governments to achieve this goal. How do you get it? So you build a site, explain your process, embed your Earth Engine app, and you have a live interactive geospatial viewer that you can let your users use it. Another interesting portal is this in Australia. They did a high resolution aerial LiDAR survey for all the coastlines and get a high resolution DM. And they say we want to let the communities themselves explore what is the risk of sea level rise. So they built this app and they uploaded the DEMs, they uploaded their data on what's the expected sea level rise based on the climate data, and they built this site. Now you can say I want to explore, I'm in this region, I want to explore. And this whole thing is an Earth Engine app. So as an Earth Engine user, you don't have to be a web developer to do this. Imagine doing this kind of slider and doing these buttons is very hard. But in Earth Engine, you just use the Earth Engine API. Say, I want a slider, I want a button that does this. So with just a simple few lines of code, you can have an interactive app. You don't have to worry about parallelization, background processing, anything. And you can build this nice, beautiful apps that are interactive. So here you can say, or look at in 2100 with this 0.747 meter rise, what buildings will be inundated. And you can say, I want to have a scenario which is not so high, which is a medium, and you can see the results will change. And this is all in the background, the processing is done by Earth Engine, and you get the interface, right? This was a recent study done by WCS in India. They were looking at the tiger reserves in India, and they wanted to see that by declaring an area protected tiger reserve, is it helping the vegetation in that area? That's a study they had. And the premise was, if you spend so much resources in protecting this region, the vegetation cover should actually improve. But is it happening or not? Right, so they did a study over 84 to 2012, where they took a bunch, I think 30 tiger reserves, and they were declared tiger reserves in multiple years, and they said, can we track how was the vegetation trending before it was declared tiger reserve, and how is it doing afterwards? And they did this study, it was published in Nature recently, and you can see the app. So again, when they publish the study in the paper itself, they given a link to this app saying you can explore this data in detail. There will always be questions, right? You go and come up with the results saying, oh, this is declining. It's like, show me. People will say, I want to really see, is your data analysis correct? Where is it declining? Can we do something about it? So this app, again, you can see this is Earth Engine, right? It's very easy to build things like this using the data set. So it's the same algorithm they're using, and they allow users to explore. So again, they are saying this is these are the protected regions, this is the areas, and you can kind of say, I want to look at this particular tiger reserve. And they have like this kind of sliders. Again, this is an Earth Engine widget. You can say, I want a split screen. Left side, I want this. Right side, I want this. You can display two maps together as an overlay. So again, this is saying that after declaration tiger, did it improve or decline, and did it help or harm? And so this is, and you can kind of see at each point and say, oh, this region seems to be harmed. What is going on? So you can click on it. It'll display, actually get all the Landsat data time series and display the time series here. See what happened. Maybe there's something happened here, right? So again, allows your users to explore this vast remote sensing data in an easy way to do this, powered by Earth Engine. This was another study done by ET3 in Bangalore. They are tracking vegetation in a protected region over a long time. So this is a time series from 99 to 15. They did classification and tracking each class of vegetation, how it's trending over time. Again, you can do this kind of time series analysis very easily. We have Sentinel-1 data, which is SAR data, which allows for water detection and flood detection easily. So one of our users built this app after the Kerala floods last year, saying, this is the before-after imagery. Which are the regions which are flooded? Can we, track that? And again, this algorithm for detection was built in Earth Engine using the Sentinel-1 data. And in using this app, you can actually interactively explore which regions are flooded, which regions are not. And you can, per administrative unit, I think per taluk, you can calculate what was the total area, which is the taluk that was affected the most, etc. IIT Bombay, anybody from IIT Bombay here? Yeah. So Avik Bhattacharya's group, they use Sentinel-1 and Earth Engine heavily. So again, this was the recent study they published for paddy detection using Earth Engine. And they are, again, they worked in West Bengal. And again, Earth Engine gives them ability to run this in a large scale, do this interesting analysis. This is not an India-specific project, but it's applicable to India. As I mentioned, people wanted us to build a system that allows people to not only see the changes, but track changes. So now we have Earth Engine. There is a non-profit that has built this operational system, which say, as a user, you can say, I'm interested in tracking forests in this region. You sign up, and every time a new Landsat scene is available, and now I think they're adding Sentinel-1 as well. So as soon as the new scene is available, they process it, compare it with the previous results, and say, oh, I'm tracking some forest loss here. You get an email alert. So this is on a real-time basis, you are able to track forests. And this is showing in Peru, the purple regions are the deforestation alert. And you can see this is on a week-by-week basis, they were able to give alerts about illegal road being constructed in the forest. And the users who were using this, they got this alert, oh, there's a road being built, there's a deforestation happening. And they were able to go and stop and catch people who were doing this, right? So real-time deforestation alert operationalized by a system like Earth Engine.
Suppose that is a forest fire. Then in that case, that can also give the alert.
I believe they have an algorithm that can differentiate fires versus the deforestation, but it's basically comparing forest loss.
Because the forest fire in Australia lasts so many
Yeah.
years.
So
Why is this technology not useful for them?
So there are people who have used Earth Engine to track forest fires as well. So forest fires uses slightly different data sets. You can use like the data set is FIRMS, which is specific for forest fires. And it will give you only the forest fire detections, not general land use detections. So it depends on the area. For example, there was a story that in Amazon, once they operationalized the system, the people who were logging, they became very smart. They say, oh, we'll log forest when there's cloud cover, because Landsat can't see in cloud cover. So when they capture a scene, they say it's cloud, sorry, we can't give an alert. Right? So the people who were developing this system said, no, we'll start using Sentinel-1, which can see through clouds. And then they caught a whole bunch of loggers who were logging during the cloud cover. Right? So again, the system is operational in I think 15 countries. And each country, the algorithm has to be slightly tweaked to the systems and the regions they have. And forest fires, I think they take care of detecting that and not giving you alert based on that. But again, the idea is that you can build a system that can give you, so the idea is, oh no, I'm not saying go and use the system, I'm saying go build a system like this that solves your problem. And Earth Engine can enable you to build this. Right? So you can now think of the possibilities. If you ever wanted to build a real-time monitoring system, and say, oh, I wish NIC would give me 100 servers, or I wish I had all this data in real time, and I wish I had 5 engineers to build this. You don't need this. Just by yourself, with all the data and the power of Google Earth Engine apps, you can build the system yourself very easily. Right? So the new, more exciting thing is integration with Tensor Flow. So Tensor Flow is Google's AI machine learning library, which allows you to run neural network models on all kinds of data set. And geospatial is a big part of it, where there are a lot of people who want to do stuff with geospatial data. So for example, if you want to say, do a classification of an image, that's kind of a classic machine learning problem. If you want to detect some areas, I want to detect cars, or I want to detect some features from imagery. What Earth Engine gives you, Earth Engine is a scalable system for global scale analysis. TensorFlow is a library for doing machine learning. When you combine both of them, you get the power of TensorFlow algorithms that can run on Earth Engine using global scale data. So the way it works is, you have Google Earth Engine. Say you want to train your model. So you say, I've manually tagged some patches and say, this is land, this is urban area, this is water. I want to train my model. So how do you get those images? Right? So Earth Engine, you can just do your training data, extract that from Earth Engine as training sets, use that in our Google AI platform, and say, train my model using all this data that I've extracted from Earth Engine. Once your model is ready, and you can refer to that model using Google Earth Engine and say, use this model and now predict. So I have a model which can detect, say, urban versus non-urban areas. that I've trained. Now I load some image, say I load a Sentinel-2 image, and say, go and find non-urban areas. Right? So you can operationalize this at a global scale using Earth Engine. And Sai is going to kind of teach you much more in detail how this whole system works, but now there's a very tight integration between these systems. So now you have a full-fledged kind of geospatial machine learning system that is accessible using Earth Engine. So Earth Engine by itself has built in the classical machine learning algorithm, so the classifications. Right? You do supervised classification. But if you want to use, say, a deep neural network for doing classification, you can use this method to do this. Right? Earth Engine is free to use. If you're not signed up, and if you want to kind of do some hands-on later today, you can sign up using this link. You need a Gmail account, and once you sign up, you can start using the system here. Right? So this is the end of my official thing. We have, I think, 15 minutes. 5 minutes? Okay, 5 minutes for questions. I can take any questions. Yeah. I think it's giving.
I have two questions.
Yeah.
The data that we are seeing in Google Earth are high resolution. The same data is available for processing in Google Earth Engine? No.
High resolution data, so again I mentioned, right? So high resolution data is not owned by Google. It's licensed from a third party provider.
Okay.
You cannot run analysis, export this. So it's just a base layer that is visible for reference, but you can't run computation on it. If you wanted to do it, go purchase your data from Digital Globe, upload it and use it.
Okay. And
Hyperion is available, yes. No, I think it's available in the catalog itself. So the way if you want to just see, if you go to Google Earth Engine, in the code, just search for this data set. Hyperion is available here. So it'll just show you what data set is available. You can refer it and start using it.
that Google Earth Engine apps that you're showing, it is published, I think it's for public, right? So it is one, if I want only for my organization, I want to build something, is it possible?
Yes, you can now, so the apps, once you build an app, this is the app publishing button. It's a new app, and here say access restriction, restrict access to this app, and it says it restricts to a Google group. So you create a Google group with the email addresses for your own organization, share it with the group, only people who are signed into those accounts will be able to access the app.
Thank you.
Yes, thank you for reminding me. One of the key things, I think when I do the training, the most useful part is showing you where to go for help. So there's a help button in the code editor. There's a user guide, detailed user guide. We have people put in a lot of effort, hours and hours of effort, documenting various features of Earth Engine. Right? There's a discussion group. So when you sign up for Earth Engine, you'll get an invitation to join a mailing list, very active mailing list, and people, you ask questions, domain-specific questions, people will answer. They'll, you know, if you're trouble running your code, you can share your code and people will help you. So just a few minutes to look at the user guide. We have tutorials, video lectures. We have guides, specific guides on, you know, how to do each thing. If I want to say, I want to do time series, how do I do time series? Right? So whole bunch of, you know, documentation that is available here. So definitely explore that and you can see more. Last question.
Yeah, using Colab.
Using Colab is the next session. Drone data, you can upload, we have seen people uploading their own drone data and then analyzing in Google Earth Engine. One quick thing that ties into the next one, I forgot to show this demo. So this is Qgis, there's a new Qgis plugin. So now you can use Earth Engine within Qgis using Python. So say this is a Bangalore boundary data. What I'm doing is, the way once you write the plugin, you can say from E plugin import map. So now your Qgis becomes your code editor. So here I'm saying same NDVI example, I'm saying run this. So I'm running this and the data is being processed in Earth Engine and you can see it's being streamed. You can see it's processing, the tiles are flowing in. Now it's in, you are in Qgis. So now I say I take this image, clip it with some local vector data and I can, when I run this, it's going to take this thing, clip this image, run NDVI and give me the results in Qgis. So now you integrate the local data versus cloud data, do remote sensing in Qgis very easily. And this is also a great place to run your Python code. because QGIS is Python-based API. So now, if you are working in Python, Colab is one way. This QGIS is another way to run your Python code and get results, right? Cool. If you want to export it, same thing works. Kick off the export from here, it goes to your Google Drive, or there's a way to download this locally and get the downloaded data back here. So JavaScript won't work because this is Python based, but JavaScript and Python all use Google API, Google Earth Engine API. So it's a very simple conversion. If you have a JavaScript, Google Earth script, you can just do some substitutions and convert to a Python script. Right, so I'm going to stop now.